Alright, this is actually part 2 of a video. I just wanted to keep them a little bit shorter because I've been having issues when I do long videos, issues with recording them. But I just got through talking about how to solve rational inequalities and equations by graphing. I did a little bit of an explanation of why it's important not to solve an inequality in the same way that you might solve an equation. For example, I don't want to just bring the x over to the other side to get like 1/3. Let's go. I'm going to just write it in here. 1/3 multiplied by x less than 5, and then bring the 3 over here to get x less than 15. The problem here is that I missed some answers, right? So at x less than 15, so let's say x is 5. Well, that's no problem. 1/3. If I check my answer, if I put in at 5 here for x, well, that is actually a solution. 1/3 is less than 5 over 5. 1/3 is less than 1. But there's some solutions I missed. Now, if you actually go to my graph, you can see those solutions that I missed. Okay, so yes, it's right that when x is less than 15, we do have a set of answers down here that are correct. But when it gets to the negatives, all of a sudden the graph is back up here. That is no longer a solution, right? Because we're looking for when it is less. When we solved it, we actually solved when this new graph is less than 0. And when you graph the rational, you actually look at it and be like, well, wait a minute, I can see that it's not less than 0 here. You have the answer sitting right in front of your face. You don't have to test a whole bunch of numbers, right? So if I had done it wrong, I could easily have said x less than 15 and tested a value, like, so okay, let's test x is 5. Be like, yeah, I'm happy with that, it works. But I'd have to test every single number before I'm like, oh, wait a minute, there are a couple numbers that don't work. But when you look at the graph, boom, you have every single number. I know exactly when the graph is below 0. I know exactly when the graph is above 0. I have all of my answers. I know when it equals 0. All right, so let's move along and solve a few more problems. Now that I've had the explanation, let's see just how quickly we could solve rational equations and inequalities. Right, let's try x plus 2 over. Oh, wait, let's try a different one first because I want to do the same order that Miss Curry did it in. So 4x minus 1 over x minus 5 equals 0, or 4x minus 1 over x minus 5 is greater or less? Let's go greater than 0. Yeah, let's do greater or equal. Why not? It really doesn't matter because we're doing it all in the same way. Pull everything to the left so that it equals 0, or so that 0 is on the right. Oh, great. Look, we don't even have to do anything because the question starts off that way. Beautiful. We can miss that step. Step 2. Get it factored. Well, it's kind of already factored. I guess we could make it nicer by taking out the leading coefficient. Just makes the zeros easier to find and the asymptotes easier to find. Okay, so we got. Notice that we always do the exact same steps with equations or inequalities. Nothing changes there. The only thing that changes is when you look at the graph where the answers are. All right, so let y, it's important to let y equal that left side so that we can actually graph it, and then we'll just take a look at it and see when that value is equal to 0. So in other words, when does it hit the x-axis? When does that value equal, when is it greater or equal to 0? Well, whenever it's on the x-axis or above the x-axis. Let's graph. We're good at these. X, y. Alright, looks like we have a 0 at, let's do the asymptotes first actually. We have an asymptote at 5. At x equals 5. It's not a whole because there's no x equals 5. There's no x minus 5 on the top. This is linear over a linear, so I'm going to have a horizontal asymptote at 4 over 1. So at y equals 4. And I'm going to have let's see what we got. 0 at x equals 1/4. 1/4. There we go. And I guess we can I think we have all our information. Let's graph it. Right, so I know I have a 0 right here. I know that it has to follow this asymptote right here. Well, there's no way to get back up to the top, so I guess it's got to go down to this asymptote, because there's no other 0 in this area, so obviously it has to go down there. And it comes from the top over here. It flips over because the bottom at x equals 5, we have an x minus 5 on the bottom, but we don't have an x minus 5 squared, so it's not going to come from the same side. It's only a single, it's an order 1 on the bottom. And then we have, it hits this asymptote, no more zeros. Right? And so we can quickly write, that was a really easy thing to do. We could quickly write 4x minus 1 over x minus 5 is equal to 0 at, right, just make sure I've got that equation right, 4x minus 1 over x minus 5 equals 0, yeah, and the answer is at, well, where does it equal 0? Right here. It's above 0, it equals 0, it's less than 0, and it flips over and it's above 0 again, and it stays above 0. It never does come back down to the x-axis. Okay, so when is it equal to 0? At 1/4. At x equals 1/4. Done. The reason it's so easy is because we're very good at graphing rationals. We can do them really, really quickly. Right? If I say 4x minus 1 over x minus 5, what was the second question I asked? Greater or equal to 0? All right. Greater or equal to 0? That just happens at, well, that's a whole bunch of different places. There's a whole interval of places. Where is it greater or equal to 0? Well, it's everywhere from negative infinity all the way to 1/4. It's above the x-axis all through here. Then it goes below for a little while, but then it pops back up above all the way off to positive infinity. Right? And it's allowed to equal as well, so 1/4 is when it equals 0. So all those spots are correct. Okay, so we're just going to say that happens from negative infinity all the way to 1/4, and 1/4 counts, so I'm going to put a square bracket to say that is actually a value that is part of it. And then again from 5, but not including 5, because that's an asymptote. So we get a round bracket all the way to infinity, round bracket. Okay, so we do have a square bracket here because 1/4 does count. We have a round bracket here because 5.000001 counts, but 5 doesn't count. 5 is undefined at that spot. All right, let's go to the next question. We're just going to zoom right through these guys. Now let's try x plus 2 divided by x minus 1. Let's say less than or equal. I'll do an inequality to start. 2x minus 3 over x plus 4. Alright, we could do the equation if we wanted as well. It's all the same. X minus 1, we could do greater than if we wanted to. Let's do an equals on the side just to remind ourselves that it works for all of these things. Okay, let's not do any multiplication or division at first. Let's do step 1 of just bringing everything to the left. X plus 2 over x minus 1 minus 2x minus 3 over x plus 4 less than or equal to 0. Here it would be the same thing, but it would be equals 0. Alright, next step. Let's get this as one single rational so we know how to graph it. We'll let y equal one single rational, right? So let's get a common denominator. X plus 4 over x plus 4 times x plus 2 over x minus 1. So x plus 4 over x plus 4 is just, will cancel itself out. X isn't allowed to be negative 4, but it's not allowed to be anyways, and we will see that on our graph anyway. Minus 2x minus 3 over x plus 4 times x minus 1 over x minus 1 less than or equal to 0. And we're going to have, so this is going to be x squared plus 6x plus 8 minus 2x squared. This is going to be minus 2x minus 6, so minus 5x, but it's minus all of that, so it's going to be plus 5x. And you got plus 3, so it's going to be minus 3. There we go, all over x plus 4, x minus 1, and that has to be less than or equal to 0. Now we're getting close. Now we're going to simplify. It's going to be negative x squared plus 11x plus 5, x plus 4, x minus 1, less than or equal to 0. Alright, this thing does not look factorable. As a matter of fact, I know it's not because I watched Miss Curry's video where she used the exact same, she had a rational equation, and it turned out that her factors looked like this. It was like x minus 11.44-ish and x plus 0.44-ish. So thank you, Miss Curry, for having done that for me. She used the quadratic equation with a is negative 1, b is 11, and c is 5, and that's how she figured that out. There we go. Now we have it factored on the top, factored on the bottom, and that is exactly how we love it to graph. Now, of course, I don't have a y variable here, so how am I going to graph x and y? Well, basically we want to know when all this here is less than 0. So let's let y equal all that. Negative, I don't think I'm leaving myself a lot of room here. That's not very forward thinking. Let's do it down here. Let y equal negative x minus 11.44, x plus 0.44, all over x plus 4, x minus 1. And now we can graph it, because now we have an x and a y variable. And then the height of this graph is simply going to be all of this. And when all of this is less than or equal to 0, that's because the height of the graph is going to be less than or equal to 0. So down here or on the x-axis. Alright, so let's do it. The bottom. We have an asymptote at x is equal to 1. Let's do that in red. X equals 1. Okay, right here. We also have negative 4. We have an asymptote at, let's say that's about here, negative 4. We have a 0 at negative 0.44. Negative 0.44. We have a 0 at 11.44. Because those are the factors on the top. And this is a quadratic divided by a quadratic, so we have a horizontal asymptote at, this is a negative 1 over a positive 1, so at negative 1 we have a horizontal asymptote. There we go. And alright, let's graph it. I know I have a 0 here, and as I go to the right, well, it's got to go down because it's got to get to this asymptote. And I know it it doesn't have another 0 just to the left of this for a while until I get to this asymptote, so it obviously follows this asymptote going up. That's a single. It's not an x minus 1 squared on the bottom, it's an x minus 1 just to the power of 1. So it's going to flip. I know I have a 0 here, so it definitely goes through there. It has to come up to this asymptote. It's going to flip over to here, and it's got to go to that asymptote. There you have it. And now we just simply look to see when it is less than or equal to 0. Okay, well here's 0 right here. So we have it's equal to 0 right at negative 0.44, negative 0.44, and at positive 11.44, and it's less than 0 from negative infinity all the way to negative 4, from 0 negative 0.44 all the way to positive 1, and over here. Anything that's below the x-axis. So there, there, and there. We don't have any holes to worry about, and so our answer is, we can just say, I'm just going to cut this out so I can, where's my original question? Okay, this is the original question we're trying to answer. So I'm going to say, therefore, this is true whenever it's less than or equal to 0. So at the interval negative infinity all the way to negative 4. That's below the x-axis there. At negative 4, it goes back, it flips to above the x-axis all the way until negative right here. So we have negative 0.44. That counts. I'm doing a square bracket here because it's allowed to equal. It's less than or equals. That goes all the way to positive 1. Positive 1 does not count because it's an asymptote. And then 11.44 will count as well. That's no problem. And it goes all the way to infinity. And infinity is not included. There we go. There's our answer. I think we asked another question over here. We said, when is it equal? Well, that's going to be a simple one to do as well. Copy. If you do it by pulling everything to the left and making it either equal or greater or less than 0, then your answer will always just be whether it's on the x-axis, above the x-axis, or below the x-axis. Placed image. And we can say, therefore, this is true at x equals negative 0.44, comma, x equals 11.44. The two places where it is equal to 0 is this blue dot and this blue dot. There you have it. Alright, do I risk doing another one? Maybe I'm going to do another video with the last one on it. Okay, so the last one, you're going to have a hole there, and I'm going to show why this graphing, again, is super convenient, because at the end, even though you should always check your answers to make sure that your answers are valid, just in case you made a mistake in your math, with this graphing method, if you didn't make a mistake in your math, you don't really have to check your answers, because all of your holes and all of your restrictions are already restrictions on your graph. They come in the form of asymptotes and holes, right? So you just wouldn't put that in your answer in the first place because you're not going to include an asymptote in the hole as a solution. So it's another really convenient thing is you don't have to go back and check your answers if you're doing your math properly. Okay, I'll see you guys again in part 3 of this lesson.